Hello, welcome to the ArXiv paper pitch on Excited Hint towards a solution of the Neutron Lifetime Puzzle. My name is Benjamin Koch, and I want to thank for the collaboration of Felix Hummel and suggestions by Hartmut Abele. So it's about the neutron decay, and the neutron can decay either from a nucleus or when it's a free neutron. And actually, this problem is about the decay of the free neutron. It can be seen in terms of Feynman diagrams or calculated in the simple quark model where the neutron consists of one up quark and two down quarks. So the free neutron has been measured, its decay has been measured in two ways, one in a neutron beam and the other in a bottle experiment. So the in-beam measurement is, as the name says, is a beam with a decay volume where when the neutron decays, proton is produced, and the proton and the electron which is produced can be measured. And counting the total beam rate and the produced protons, you can deduce the lifetime. And this is what happened or has been done, and the result was 888 seconds, plus minus 2. In contrast, the bottle measurements work with ultra-cold neutrons, which means that they have neutrons which are only of 5 meters per second, roundabout, much slower. And since they are so slow, they can be trapped either in solid wall bottles or in magnetic wall bottles. Independent of that, the strategy is filling the bottle, waiting a while, and counting before and after. And from this, you can deduce the decay rate and the lifetime. And the result is a different one, so 879 seconds. And if you make a comparison of both results or types of experiments and their results, you see the red, you see the beam, and the blue region is the bottle. And the average distance is of 8.6, almost 10 seconds. This corresponds to a 4.4 sigma discrepancy, which of a number which should be actually the same, because the same free neutrons. So, of course, this has been around for a while, so there are many approaches and ideas on the market. Many of them are quite exotic and have been either strongly constrained or even excluded. There's also a debate on the systematic error, in particular in the beam experiments, but also this has been refuted in the last year. So by many, the beam is just ignored, or the beam result is ignored. But okay, let's take in serious the work and results of our experimental colleagues and try to think about this problem. So what does really make the difference between beams and bottle? Well, first of all, there's the velocity. In a beam, the neutrons are around about 2000 meters per second. In the bottle, it's only 5 meters per second. So that's a difference, but it's far too slow too small to think about relativistic or any effect like this. Another difference is magnetic fields. So they are of different magnitude, depends on the experiment, and it's hard to imagine an explanation here. So what we want to, or I want to raise your attention to is now that the time is different, that the bottle experiments and the beam experiments are made at a completely different time scale after the production of a free neutron in a nuclear decay or nuclear reactor. While the beam is close to the reactor with the freshly coming out neutrons 20 milliseconds after basically their production, the bottle experiment is done much later after a process of cooling and whatsoever, about 300 seconds later. So what could probably happen? Well, here is the hypothesis, which is part of the paper. Let's imagine that there exists for the free neutron a slightly excited state, which is written here at psi e. And this state has gone unnoticed. It's slightly different from the ground state of the free neutron. So what you measure when you measure the decay rate in weak decays is, of course, the admixture of the excited and the ground state. So if the excited state can relax in a certain time to the ground state, and if the weak decay rate of ground state and excited state is different, you can actually measure different results at different times. So this would be the observable and the total number of neutrons divided over the rate of decay of neutrons, but this is the total number of neutrons. And that would be, of course, a variable number in time. So how could that work? You need certain conditions to be fulfilled. And let's list these conditions. So first of all, you need two different states, Psi and Psi ground state. You need the energy splitting between the two, not too big, because you need to produce it in the nuclear decay. So far smaller than 10 mega electron volt. You need a beta decay, which is different for the excited and the ground state. And the strange thing is that the excited state should actually live longer than the ground state. You need that the electromagnetic transition happens somewhere between the beam and the bottle, which is somewhere between 20 milliseconds and 300 seconds. And then you also need the right abundancy, and you need that the excited state is not produced within the nucleus, because otherwise it would have been seen. So how can that happen? Well, we cooked up a toy model. So here again are the conditions we put on the toy model. And here is the result for the little toy model of the condition for the whole thing to work. And we see it was quite successful here. And as I said, the electromagnetic decay in the toy model is more pushed to the bottle time. So this is all I wanted to tell you. So the Neutron Lifetime Puzzle is a very interesting problem in particle physics. We proposed a new ansatz, which consists of considering a hypothetical excited state, which is not beyond the standard model, but it's just standard interactions actually considered. And we also presented a little toy model where most of the features needed are present. So what is to do? Well, of course, one would need a better and more precise models. And even more importantly, one could do a number of experimental tests to refute this idea or support it. So this was everything I wanted to tell you in this paper pitch. Thank you very much. And more details can be seen in the paper.